momentum is a very simple quantity. It is simply the mass of an object multiplied by the velocity of that object. So we abbreviate momentum with a P. Don't ask me why, but we do. Mass is an m, v is velocity. Momentum is measured in a unit. Well, mass is measured in kilograms. Velocity is meters per second. So momentum must be kilogram meters per second. As simple as that. It turns out that kilogram meters per second is the same as Newton seconds. And let's just look at that for a second. What is a Newton measuring? It's measuring force. Force is equal to mass times acceleration. So we know that a Newton, if we look at the units, is a kilogram, and acceleration is meters per second squared. So if I look at a Newton second, I've got kilograms meters per second squared from there, multiplied by a second, and that is equal to kilograms meters, and s to the minus 2, s to the invisible 1 is going to be s to the minus 1. So they're exactly the same thing. What's important is that momentum is a vector quantity. A vector quantity means that you have to consider the direction, and the direction of the momentum is always the same as the velocity. The faster an object moves, the greater its momentum. Well, that's not surprising. Momentum is the tendency of an object to continue or maintain its state of motion. So if something is very, very fast, it will tend to continue moving. And if something is very, very heavy, it will also tend to continue moving. Momentum is the tendency of an object to maintain its current state of motion, which sounds a lot like Newton's first law, which says that an object will remain at rest or at a constant velocity unless an unbalanced force acts on it. In other words, it will stay in its current state of motion. So, simple. Calculate the momentum of a 500-gram toy. The only thing we need to do is change that into 0.5 kilograms. Train, and it is moving at 0.3 meters per second in a westerly direction. I simply multiply the mass times the velocity, and I land up with a westerly momentum. Nothing difficult in that. However, obviously it doesn't stay that simple, otherwise it wouldn't be in the matric curriculum. So what we're going to take a look at is what happens when we have got objects that collide. So we're going to look at collisions. In any collision, the total linear momentum in a closed system remains constant. Linear momentum means that I'm going to only work in one dimension. In other words, the momentum before a collision is equal to the momentum after collision. So we've got these two little cars, and they're moving towards each other. Before they collide, they've got a mass, both of them, and they've also both got a velocity. Now they bash into each other and they separate afterwards. Look at the arrows going in opposite directions. They've got a mass and a velocity. I've made the initial velocities little u's, and I've made the final velocities little v's. It's not quite the same as initial and final velocity in equations of motion, but I like to think of a before and after start, end. And start is little is a u, and v is for a final velocity. And all I do is I add up all the momentum before. The mass times the velocity of the first object plus the mass times the velocity of the second object will be equal to the mass times the velocity of the first object plus the mass times the velocity of the second object after the collision. Not difficult. What about if the two objects stick together? Here they come along with their two separate masses and velocities. I add those together before. Afterwards, their masses combine and there's a new velocity. So you then combine their masses and they've got a single velocity after the collision when they've stuck together. How about if the two objects were stationary to begin with and they explode apart? Boom, boom. So that's a spring, pow, pow. And you then got afterwards mass times the velocity plus the mass times the velocity. Well, how can that equal 0? Well, obviously one of the velocities is in the opposite direction, so it will get a negative sign and then you will land up with 0. Let's see what we get. We've got a trolley of mass 3 kilograms, 3 kilograms, 3 kilograms. It travels east along at 7 meters per second. That's before the collision. Trolley B, 4 kilograms, is going on the same path in the same direction at 12 meters per second. So there they are. Then I am going to, after the collision, after the trolleys collide, A continues to travel in the same direction at 11 meters per second. What is the velocity of B? So I've got the mass of B. What is its velocity? I'm going to choose a sign convention. I'm going to say that east is positive, and every time I've got an easterly velocity, I'm putting a positive number in. Turns out once I resolve this whole thing, I land up with a positive number again. So in other words, it would be 9 meters per second east. If I got a negative number, it would be west, but it's not. Notice a few things. When I'm doing conservation of momentum, I need to say that the momentum before the collision is equal to the momentum after the collision, or the total linear momentum is conserved. Something along those lines. Otherwise, this makes no sense at all. You need to substitute into something with meaning. We've got a space capsule, and it's at rest in space. It's 1,000 kilograms. At rest means it's standing still. With respect to a meteorite of 2 kilograms that's going hurtling at 2,000 meters per second. The meteorite combines with the capsule. So you then combine their mass, so they become 1,002 kilograms, and they've now got a combined velocity. Turns out it also lands up with a positive value, which means that whatever direction the first object, the meteorite, was moving in is the direction that the combined system is moving in. Notice I've said momentum before is equal to momentum after before, just writing all those numbers down. And what direction is that happening? In the direction of the original meteorite's movement. I've got a stationary 150 kilogram cannon, and they're all stationary, so everything's still at the beginning. Momentum before is 0, momentum after is going to split out, and the cannonball goes at 65 meters per second. And when I resolve this out, the cannon's 150. When I resolve this out, I find I get negative 1,3 meters per second. What does that negative mean? It means that it goes in the opposite direction to the cannonball. We need to know something about elastic and inelastic collisions. Basically, we don't really need to now, because conservation of momentum holds true for both types of collisions. So it doesn't matter if it's elastic or inelastic, but they are going to end up asking us questions soon about whether it's elastic or inelastic. Generally, in inelastic collisions, the object will change shape permanently. They don't just bounce off each other. So an elastic collision is basically a bounce in which nothing changes. There's no permanent deformation. The objects just separate after the collision. Whilst in an inelastic collision, you've normally got them sticking together, everything changes shape. The big thing that you're going to have to calculate eventually is that the kinetic energy for an elastic collision is equal to the kinetic energy afterwards. Does something like this exist? Not really. So generally every collision will have some energy being lost, but in ideal circumstances, maybe somewhere in an exam question, you will find that the kinetic energy before was equal to the kinetic energy after. If they're not equal to each other, then you have got an inelastic collision.